This is Catherine Schmer at Chattanooga State Community College. This video covers the topic of double integrals over general regions for Calculus 3. In the last section, we discussed double integrals over rectangular regions. Recall that to find the volume under a surface over a rectangular region in the xy plane, the function of x and y that describes the surface is the integrand, and the x-bounds and y-bounds are constants. In this section, the function of x and y will still be our integrand, but either the x-bounds or the y-bounds will be a function of one variable. When we want to find the volume underneath a function f of xy over a non-rectangular region, we adjust our bounds of integration to be a mixture of functions and constants. We should always have constant bounds on the outer integral. For example, say that I have a three-dimensional surface, f of xy, above the xy plane. I want to find the volume underneath the surface over a circular region, D. In order to do this, I would need to express the region D in terms of x and y functions, with one variable expressed as a function of the other and the independent variable expressed by constant bounds. The function f of xy would be the integrand. Our first example asks us to integrate the function f of xy equals x divided by y over the quadrilateral region with vertices 1, 1, 1, 2, 2, 2, and 2, 4. The first thing that we want to do is to picture the two-dimensional region in the xy plane that is described in the problem. I start by plotting the given points in the xy plane and connecting them with straight line segments. I then shade in the region. With this quadrilateral, it is easiest to define a lower bound and upper bound for y as a function of x. If I tried to define a left bound and right bound for x as a function of y, then the region would have to be broken up into two pieces. So it will be more straightforward to use constant bounds for x and write the y bounds as functions of x. We will start with the upper y bound, which is the line between the points 1, 2, and 2, 4. We can determine the slope by calculating y2 minus y1 over x2 minus x1. In this case, the calculation is the quantity 4 minus 2 divided by the quantity 2 minus 1, resulting in a slope of 2. Using the point 1, 2, we plug our numbers into the point slope form of the line, resulting in y minus 2 equals 2 times the quantity x minus 1. Solving for y gives us the function y equals 2x. To get a lower bound for y, we use the same process with the points 1, 1, and 2, 2. The slope is the quantity 2 minus 1 over the quantity 2 minus 1, giving a slope of 1. Plugging in the slope of 1 and the point 1, 1 into the point slope form of a line gives y minus 1 equals 1 times the quantity x minus 1. Solving for y, we get y equals x as the lower bound of the region. So we have calculated that y goes from x to 2x. Since the y bounds are expressed as functions of x, we know that the bounds for x must be constants, since the outer integral must have constant bounds. We can see from our shaded region that the left bound for x is 1 and the right bound for x is 2, so we say that x goes from 1 to 2. The constants must be the outer bounds of the integral, so we know that the order of integration will be dy dx. The function f of xy equals x over y is the integrand. So the volume under the function over the given quadrilateral is v equals the integral from 1 to 2, our x bounds, of the integral from x to 2x, our y bounds, of the integrand x over y, our function, dy dx. Since the inner integral uses y bounds and the outer integral uses x bounds. Now we need to integrate to find the volume. We focus on the inner integral first with respect to y. Treating x as a constant times 1 over y, we get x times the natural log of y evaluated from y equals x to y equals 2x. We still need to write the outer integral, x going from 1 to 2, since we have not dealt with it yet. Using the fundamental theorem of calculus, f of b minus f of a, we get x times the natural log of 2x minus x times the natural log of x. We can use the log property natural log of a minus natural log of b equals natural log of a over b in order to simplify the new integrand to x times natural log of 2x over x, which simplifies to x times the natural log of 2. We now need to take the integral from 1 to 2 with respect to x of x times the natural log of 2. Since the natural log of 2 is a constant, we can pull it out front. We now have the natural log of 2 times the integral from 1 to 2 of x dx. Integrating this gives us the natural log of 2 times x squared over 2 evaluated from x equals 1 to x equals 2. We plug in the upper bound and lower bound for x and subtract, giving us the natural log of 2 times the quantity 2 minus 1/2, which simplifies to 3/2 natural log of 2. So the volume under the surface of f of xy equals x divided by y over the quadrilateral region with vertices 1, 1, 1, 2, 2, 2, and 2, 4 is 3/2 natural log of 2. Example 2 asks us to find the volume of the region bounded above by the cylinder z equals x squared and below by the region enclosed by the parabola y equals 2 minus x squared and the line y equals x in the xy plane. We know that our z function will be the integrand, but I always start by graphing the region in the xy plane because that region will define the bounds of the integrals. We start by graphing the line y equals x. Next, we need to find the points of intersection of y equals x and y equals 2 minus x squared. Setting the two equations equal, we have x equals 2 minus x squared. Bring all terms to the left side of the equal sign to get x squared plus x minus 2 equals 0. This quadratic factors as the quantity x plus 2 times the quantity x minus 1 equals 0, which produces the solutions x equals -2, and x equals +1. Using these points of intersection, we graph the upside-down parabola y equals 2 minus x squared, with the parabola crossing the line y equals x at the points 1, 1 and -2, -2. Shade in the region and use it to find the bounds of integration. Y goes from lower bound y equals x to upper bound y equals 2 minus x squared, and x goes from x equals -2 to x equals 1. We know that the integrand is the cylinder z equals x squared, since we were told that the region is bounded above by this surface. We now have all the parts to set up our double integral. The constant x bounds must be on the outer integral, so we have that the volume equals the integral from -2 to 1 of the integral from x to 2 minus x squared of the integrand x squared dy dx. Now we work our way inside outward, so we are integrating with respect to y first. With respect to y, we treat the integrand x squared like a constant. We still need to write the outer integral from -2 to 1, since we have not done anything with it yet. The integral with respect to y of x squared is x squared times y, evaluated from y equals x to y equals 2 minus x squared. Then we will still have the dx on the end, since we have not done anything with it yet either. Using f of b minus f of a, the new integrand is x squared times the quantity 2 minus x squared minus x squared times x. We want to simplify before integrating with respect to x. Now we need to find the integral from -2 to 1 of 2x squared minus x to the 4th minus x to the 3rd dx. We use the power rule to get 2/3 x cubed minus x to the 5th over 5 minus x to the 4th over 4 evaluated from -2 to 1. Plug in the upper bound of 1, then the lower bound of -2, and use f of b minus f of a, and we get a volume of 63 over 20 cubic units. Example 3 is a little trickier than the previous two examples because one border of the two-dimensional region will be defined by a three-dimensional function. We are asked to find the volume of the solid in the first octant bounded by the coordinate planes, the plane x equals 2y, and the cylinder y squared plus z squared equals 4. Recall that the first octant is where x, y, and z are all greater than or equal to 0. The coordinate planes refer to the planes x equals 0, y equals 0, and z equals 0. Let's try graphing the two-dimensional region that will define our bounds of integration along with the three-dimensional region that we're finding the volume of. I have my x, y, and z axes on the left side of the screen and my two-dimensional x and y axes on the right side of the screen. I start by graphing the two-dimensional line x equals 2y, which passes through the points 2, 1 and 4, 2. I'm also going to put this line in the xy plane of my three-dimensional grid. Now we need to look at the equation y squared plus z squared equals 4. This is a cylinder of radius 2 parallel to the x-axis, but we only want the portion in the first octant. I graph this on the three-dimensional grid. We're told in the problem statement that the cylinder is one of the bounds, so I shade in the region in the xy plane bounded by the line x equals 2y, the y-axis, and the edge of the cylinder. The edge of the cylinder in the xy plane is the line y equals 2, so now we can figure out all the bounds of the region of integration. Since we have the three-dimensional graph, let's look at the region that we will be finding the volume of. We know that in 3 dimensions, the equation x equals 2y is a vertical plane, so it will slice off a portion of the cylinder. The lower bound of the region is the triangular region in the xy plane that we found in the last step, and the upper part of the three-dimensional region is bounded by the cylinder. This results in a small wedge of the cylinder that we will find the volume of. Looking at our two-dimensional region of integration, we can determine that x goes from x equals 0 to x equals 2y. Since x is expressed as a function of y, we must have constant bounds for y. Y goes from 0 to 2. The integrand will be the function involving z, which in this case is the cylinder, y squared plus z squared equals 4. We need to solve for z. Z squared equals 4 minus y squared, so z equals the square root of 4 minus y squared. We only need the positive root because we're in the first octant. Putting it all together, we get the volume equals the integral from y equals 0 to y equals 2 of the integral from x equals 0 to x equals 2y of the integrand 4 minus y squared to the 1/2 dx dy. Note that I just rewrote the square root as a 1/2 power. To evaluate the inner integral with respect to x, the entire integrand 4 minus y squared to the 1/2 is considered a constant, since there is no x involved. We get the integral from 0 to 2 of quantity 4 minus y squared quantity to the 1/2 times x evaluated from 0 to 2y dy. After plugging in the upper and lower bounds for x, we get the integral from 0 to 2 of 2y times the quantity 4 minus y squared quantity to the 1/2 dy. We need a u substitution to evaluate the integral. Let u equal 4 minus y squared, then du equals negative 2y dy. We want to replace the factor 2y dy in the integral, so we solve for it and get negative du equals 2y dy. Now let's change our bounds. The lower bound is y equals 0. Plugging this into u results in u equals 4 minus 0 squared. So the lower bound with respect to u is 4. The upper bound is y equals 2. Plugging this into u results in u equals 4 minus 2 squared, which is 0. So the upper bound with respect to u is 0. So our integral with the u substitution is the integral from 4 to 0 of u to the 1/2 du. We can pull the negative out front. The negative came from the negative du, which replaced 2y dy. Integrating, we get negative 2/3 times u to the 3/2 evaluated from u equals 4 to u equals 0. Plugging the upper and lower bounds results in negative 2/3 times the quantity 0 to the 3/2 minus 4 to the 3/2, giving us a volume of 16/3 cubic units. Hopefully these 3 examples have given you a good feeling for how to set up and evaluate double integrals to find volume. Next, we're going to practice switching the order of integration. Just as when we were integrating over rectangular regions in the last section, we can change the order of integration when integrating over a non-rectangular region. The theorem on reversing the order of integration, known as Fubini's theorem, states that if f of xy is continuous on a region R, then the double integral of f of xy over R is equal to the double integral of f of xy with outer integral from x equals a to x equals b, and inner integral from y equals g1 of x to y equals g2 of x. This is equivalent to the double integral of f of xy with outer integral from y equals c to y equals d, and inner integral from x equals h1 of y to x equals h2 of y. Example 4 asks us to sketch the region of integration and write an equivalent double integral with the order of integration reversed. Part A gives us the double integral of dx dy with inner integral from x equals y, the left bound of the region, to x equals square root of y, the right bound of the region, and outer integral from y equals 0 to y equals 1. To graph this, we'll start with the line x equals y. Then we'll graph the parabola, or half parabola, x equals the square root of y. We know that these graphs intersect at 0, 0, and 1, 1, and then we shade in the region. Since our goal is to switch the order of integration, we want to find a lower bound and upper bound for y in terms of x. Solving the equation x equals the square root of y for y, we get y equals x squared for the lower bound. For the upper bound, we have x equals y, which when solved for y becomes y equals x. So now we have a lower bound of y equals x squared and an upper bound of y equals x. We can tell from the shaded region that x goes from 0 to 1. Putting all of this together, we have the double integral of dy dx with inner bounds y equals x squared to y equals x, and outer bounds x equals 0 to x equals 1. Part B of example 4 gives the double integral of sine of x, 6 sine of x, gives the double integral of 6x dy dx with inner bounds from y equals the negative square root of 4 minus x squared to the positive square root of 4 minus x squared, and outer bounds from x equals 0 to 2. We can ignore the integrand z equals 6x, since this will remain the same even after we switch the order of integration. To graph the region R, start by focusing on the functions y going from the negative square root of 4 minus x squared to the positive square root of 4 minus x squared. This is the lower and upper halves of a circle of radius 2 centered at the origin. If needed, you can always use your calculator to graph the bounds. Next, since we're given that x goes from 0 to 2, we shade in the right half of the circle. To switch the order of integration, we want to express x as a function of y. We know that the circle we're looking at has the equation x squared plus y squared equals 4. We only want the right half of the circle, which is expressed by x equals the square root of 4 minus y squared. So x goes from 0 to square root of 4 minus y squared. We can see from the shaded portion of the circle that the smallest y value is negative 2 and the largest y value is positive 2, so the y bounds are negative 2 to 2. Our double integral with the order of integration reversed is then the double integral of 6x dx dy with inner integral from x equals 0 to the square root of 4 minus y squared, and outer integral from y equals negative 2 to 2.